Hey everyone, on this lesson we are going to solve the problem 8 on this laboratory 2 on signals and process communication. This problem 8 states, download the weight PAD1.c file available in the resources of this lesson. We can download this file from the downloadable documents of this lesson. And then this problem says, create a copy of this program, weight PAD1, code now example signal.c and modify it so that the parent process reprograms the sick child signal. Okay. The treatment of the sick child should execute the wait PID function without blocking the parent process. So, thus enabling the parent to monitor if any child process has ended and continue with its normal execution. Now, recall that and keep in mind that in this case, okay, an active wait must be added to the parent process so that it does not terminate prematurely. However, this option is usually used when the parent has other tasks to perform. To determine if there are any child processes still running, a global variable can be utilized. Okay, very well, so let's begin by opening this file, waitpad1 that we are given with. So here we have this file. Remember, this is not the first time that we see this program, waitpad1. Right? In fact, in the problem 5, we already saw this program and work with this file. So essentially, we can see that in this program, what we do is we have the parent process. Okay? The parent process will create a total of 10 children. This creation is going to be in a concurrent way, in the sense of the parent process will create 10 children, and then at the end it is going to wait for all of them to terminate. Moreover, what we do inside this program as well is we here modify the treatment of the SIG alarm signal. Remember, if we have a process and this process receives the SIG alarm signal, the default behavior, the default treatment is to terminate this process, right? We already saw this, that when we have a SIG alarm signal, essentially what we see in the output on the console is alarm clock, and then the process terminates. So here we modify this. Okay, remember, to modify a signal, we always need to work with the SIG action structure and also the SIG action function. So we define a new SIG action structure, we also define a mask, we also, here very important, we avoid receiving a SIG alarm, okay, outside the SIG suspend. So to do this, we create an empty set inside this mask. So for now, this mask has no signal inside. We add the SIG alarm signal to this mask with the SIG add set function, and finally we use this system call, which is the SIG proc mask, and what we do is we block all of the signals that we have inside this mask. So since in this mask we only have the SIG alarm, we are only blocking the SIG alarm signal, okay, to be received outside the SIG suspend. So then we begin by creating, and we begin this process of creations all of the children, right? What is important to notice here is that only the parent is going to create children here. The child, okay, every child that we have inside this program is not going to create any other process. The only process that creates here new processes is the executable one, the original one, which is the parent, right? The parent is going to create in total 10 children because we have in total 10 iterations inside this loop, right? So what we do is we basically here make a display to here indicate the user that we're creating a child. So we're creating the child number, and here we have the number of the child, right? We are going to have from 0 to 9, so in total 10 children. And now what we do here is we can basically set the code for the child, okay? Remember that when we do a fork system call, this is the system call that creates a new process. So this is how we create new children with the fork. And this system call returns 3 different values, okay? The first possible value is 0. If the fork system call returns 0, it means that we are the child. The second possible value is that the fork returns a value greater than 0, and precisely this value greater than 0 is the PID of the child that is sent to the parent. So if we have a value greater than 0, it means that we are the parent. Finally, it can also return -1. So if we have this value less than 0, right, smaller than 0, it means that there was an error, right? So if the fork system call returns -1, we have an error. In fact, here we can manage this error case. So if there was an error in the fork, right? So if the PID, basically this returning value of the fork, if this variable is less than 0, so if it is -1, for instance, we have this error in the fork. So we can use here the function error and exit, which is a very short and simple function that we've been working a lot through the course, right? Basically, given a message, giving an exit status, we print this message through the console and we exit the program with this exit status. Commonly, when we have an error, the exit status is 1. That's why here, when we have an error, okay, in the sig action, we are going to get to this code in a moment, we exit with 1. When we have an error in the fork system call, here we also exit with 1, right? So now, this is the case if there was an error in the fork, okay? This will likely never happen. So now what about if we are the child? So what if the fork here returns 0? So essentially here, if we are the child, what we do is we here modify, and we modify the treatment of the SIG alarm. So this is done, very important. This modification of the table of signals, this information that we have, okay, the treatment for each signal, okay, we have here different treatment if we are the child or if we are the parent. Keep in mind that we are changing the treatment for the SIG alarm in the child. So here, every child at each iteration of this loop, right? Every child, because the PID is 0, is going here to basically set the treatment of the SIG alarm to be this function. And what we do inside this function? Well, we can see that we don't do anything, right? We basically have this procedure, treat alarm, we don't do anything. So here, what we have is that each children is going to receive the SIG alarm, okay? And this SIG alarm will not terminate the children. Keep in mind that we are not going to terminate the children. We are going to execute this procedure that does nothing. Here we can do this by, first of all, defining the structure SIG action handler to be this function that we want. So essentially, instead of doing the default behavior of the SIG alarm, which is to terminate the process and printing the alarm clock in the console, what we do now is to execute this procedure, right? Then we also need to modify the flags. Now, normally we will use the SA restart, this structure SIG action restart, basically indicates that if we have a system call that is paused because of the receival of a given signal, such system calls commonly are the write and the read system calls. So what we are going to do is, after treating the signal, we are going to restart these system calls. Okay, so mostly this is going to be the case where we have. Finally, we here set the mask of the structure SIG action to contain all of the signals. And finally, the most important part, and this is where we here modify the treatment of the SIG alarm, is using the SIG action function. So on one side, we have the structure SIG action, and on the other, we have the SIG action function. It is, okay, strongly the SIG action function that modifies the treatment of the SIG alarm. And so what we do is we type SIG action. The first argument is the signal we want to modify the behavior of, right, when we receive it. The second argument is this structure that we have, the SIG action structure that we pass by reference. And the third value is the old SIG action value. So since we only have one SIG action structure, the only and unique one, right, we're not interested in here saving the status of the old SIG action. So we can just set this argument to be null, right? Here in the same way, we can, and it is here a very good practice to handle possible errors. Although, unless we have any error of the implementation on the operating system, this will not be the case. The SIG action will always work. But it is important here, if this returns -1, okay, the SIG action function returns -1 if there was an error executing this function. So if this happens, we are going to error, basically to exit the program with this exit status 1, which stands for errors, and the message is going to be SIG action, right? Then we are the child. We modify the behavior, right, of the SIG alarm. Then what we do is we print, hi, I am, and then I have the PID of the child. We can get the PID of a process with the get PID system call, right? So what we do here is we save this string inside this buffer, and with this system call write, we write on the standard output, which is the channel 1. Whenever you type here at the channel 1, this is the standard output, the console, the terminal. We write this buffer, and we're going to write all of the bytes of this string. So here we have the string length of this buffer, right? And then, very important, we set a timer of 1 second to receive the alarm. So here each child is going to wait 1 second, or basically in 1 second, okay, the timer is going to send this SIG alarm to the child, right? So we program the timer to be 1 second. Then here, what we do is we need to suspend the child to wait for this arrival, to wait for this receival of the SIG alarm. So to do this, first of all, we create a mask, okay, where we have all of the signals blocked inside. We can do this with the SIG fill set. What we do here is we fill this mask with all of the signals inside to be blocked. And when a signal is blocked, we are not going to treat this signal. So since we want here to treat the SIG alarm signal, right, this is an interest here in this program, we are going to delete from the mask of blocked signals the SIG alarm signal. So we delete this from this mask. Moreover, it is also here a very good option to be able to finish this process very easily. And one possible way of finishing a program is typing Ctrl+C. If you type Ctrl+C, what you're doing is you're sending the SIGINT signal to this process, and the default behavior of the SIGINT is to terminate this process, right? So this is the command Ctrl+C that we see. Okay, we want this to be possible as well, so we remove this signal from the mask of blocked signals. Very well, so finally we here suspend this child. So we have the SIG suspend where we wait for the arrival of one of these two signals. And finally we terminate the execution of the child, very important, with the 0x status. Okay, so here the status for this exit is 0 because this is an exit without any errors at all. If we have no errors, the exit status will always be 0. Very well, so this is the code, right, for the child. Now what about the parent? Well, here the parent is going to execute this code, okay? Keep in mind that this is done already outside the for loop, so once we finish the creation of all of these children, the parent, what is going to do, this is very important, only the parent executes the following code, only the parent, right? So what is going to happen is the parent is going to wait while there are still children, okay, here alive, we are going to wait for their termination. And a very easy way to do this is by using the waitPAD system call. Remember, waitPAD, okay, the waitPAD system call allows us to wait for the termination of any child or a specific child if we want. This first argument, -1, specifies that we are going to wait for the termination of any child. We are not interested in which one, okay? It is enough that it is a child of ours, we are going to wait for its termination. We can also here type the PID of the child that we want, in a specific PID, okay? But this is not the case. We want here to wait for anyone, right? So on the second argument, we have this result. This is how the child has finished. This is information of how the child has finished. We already saw previously in this course problems about this, where we can here get if the child terminated within a signal or if this child terminated with a common exit status, right? This is the result. And finally, this last value 0. So this last argument, the third one that we see here of the waitPAD function, okay, is the options argument, right, which we already studied, which allows us to specify various options for the waitPAD. In this case, the 0 value in this third argument means that the function will operate in its default mode. Here, this basically means that the function will return immediately if any child process has terminated. Okay, so then what we do is we save this string into this buffer and we print it, and what we print in this message is terminates the process and then the PID of the child. Keep in mind that the waitPAD, the returning value of this system called the waitPAD, is the PID, the process identifier of the child that has finished. So here we will have this information, so we can basically notify the user which child has finished at that moment. So whenever a child finishes, okay, we print it to the user, and also we need to decrement this variable, okay, in 1, because here we are going to do this unless we get the value equal to 0. So we are going to finish. It means that all of the children have finished, right? So we here, for each child that finishes, we decrement this value. And also we increment the value of the counter. This is merely here to check how many children we have created so far. And at the end, we print this value of this counter, right? Basically specifying how many children we have created inside this program. Very well. So for now, let's run and let's execute this code, okay? And then we are going to modify this code. We are going to create the example signal program. We are going to there modify the treatment of the sick child signal, right? So first thing we need to do is we open the console of our operating system, and then we place ourselves, we move to the directory where we have this file. So in our case, we have this file waitpad inside documents, then we have inside this folder lab 2 operating systems, then we have the folder problem 8, and inside this folder we have this waitpad. We can list the contents of this folder with the ls command, and here we see the waitpad1. Right? So let's compile it. We can easily compile a C file with the gcc-o. Let's name the executable to be the same as the name of the file, and here we have the name of the file. Right? So we press now the enter key. Very well. Now we can see that here we have created and we have the executable file. Let's run it. With the pond, and then we have here the slash, okay, basically a dart and a slash, and then the name. So the name is waitpad1. We press the enter key, and here we can see, okay, the output. So what we do is the parent is going to essentially print these messages, creating the child number 0, creating the child number 1, and so on. And we have here a concurrent program. It is concurrent because the parent creates all of the children, and then it waits for all of them to finish. So it's not something like, I create the child number 0, I wait the child number 0 to finish. Once this child has finished, I create the child number 1. Okay, and then I wait the child number 1 to finish. Once the child 1 has finished, I create the child number 2. This is something that is called a sequential scheme, okay, of process creation. This is a concurrent scheme. We create all of them, and then we wait for the termination of all of them, right? So that's why we here say that this is concurrent. So of course, what is going to be the child number 1? In this case, the child number 0 PID. Well, very easily we can see that the child 0 PID, the first one that is created, has this PID in here, right? Which is the PID 229. We know this because this is the smallest value. Then this is the child 1, child 2, and so on, right? We get here the PIDs, they are increasing as we keep creating all of these children, right? So the idea is we now, once we have created all of the children, we wait for the termination of them. And here we can see the order of termination, okay? The order of termination is also something that is stochastic. It is a stochastic because we cannot predict this. So we here see how they finish, okay? As we can see, we begin by finishing these ones, but then we have another order, then this is also changed, and so on, right? At the end, the parent process basically prints the value of the counter, which is how many children we have created so far. If we execute this program again, waitpad1, okay, here we see the termination. Okay, now it seems to be all in order, but if we execute again, okay, now we here see also the display is different. We execute it again, okay, and we see that this is something that is a stochastic, of course, right? So very, very important. This is a concurrent program that we create all of the children being the parent, and then we wait here for the termination of all of them. Now, once we have introduced this code, okay, here what we need to do is to create a copy of this program. So we are going to create a copy called the example signal. And what we need to do now, we need to modify the parent process. So it is going to be only the parent that is going to reprogram the sick child treatment, right? This treatment of the sick child should execute the waitPID function without blocking the parent process, enabling this parent process to monitor if any child process has terminated, and also to continue its normal execution. Right, so let's see how we can do this. So first of all, we create a copy of this file. We name this copy to be example signal, as the program statement specifies. So let's begin by reprogramming the sick child signal inside the parent process. Okay, inside the parent process. So to do this, changing the treatment, we need to change here the treatment of the sick child. So here we can begin by defining the handler. We are going to define a new user specified function when a sick child arrives, right? So we can basically use this same structure, sick action, as a handler. Let's say that this is equal to the treatment of the death of the child, okay, like this. So we're going to define this user specified function when we receive the sick child. Once the child has terminated, right, what we are going to do. Also the flags, we're going to use the same ones as always. The structure sig action restart to restart the system calls, right? We also here fill all of the mask with all of the signals inside the structure sig action. So sig fill set of this structure sig action of this structure sig action mask, right? And now we use the sig action child, right? So we can simply use here sig action, which is the function sig action, right? Sig child, the structure sig action, and the null value, because we don't want to hold the old value information. And with this, okay, with this we are basically reprogramming the sig child signal. Is this an oath? Yes, of course this is an oath. However, okay, for what it takes, it is very important, a very good practice to always consider the case, the errors that might happen inside the system calls. Okay, it may happen that the operating system, okay, has a wrong implementation in a current moment, or the stack has overflow, okay? So whenever happens with the system call, it is a good practice to always handle the case for errors. So here, if this value of the sig action returns -1, we can check if this value here is less than 0, it means that there was an error. So if there was an error, we are going to execute the error and exit function, and here we are going to pass the message sig action, right? So here the error message is sig action, and the exit status is 1. So in this case, if the sig action returns -1, we are going to execute this error and exit procedure, right? Very well. So with this, we reprogram, right? We are reprogramming, with this here, we are reprogramming the treatment of the sick child signal. Remember, whenever a child terminates, this child sends, or the kernel sends, a sick child to the parent, right? To the parent of this child, with the information of who is this child, okay, and also the cause of its death and so on. So, very important as well, since we want to avoid receiving the sig alarm before the sig suspend, we also want to avoid receiving the sig child here. So also in the same way, okay, also we avoid receiving the sig child. Here we can basically add to this set this sig child signal. So we just type sig add set, here we type to this mask, and here we type the sig child, right? And with this, we are blocking the sig alarm and the sig child to be received outside the sig suspend. Okay, so this is the code of the parent. Remember that this statement specifies that we only need to reprogram the sig child on the parent process, right? So when it comes to the code of the child, we are going to have the same code. We are not going to modify anything of this, neither of the error case, right? What is important also here, the most important part, right, is that here this active waiting is going to be different because it is inside the treatment, and this is important. It is inside the treatment of the sick child where the wait PID is going to take place. Note that here it is specified that the treatment of the sick child should execute the wait PID function, right, without blocking the parent process, enabling the parent to monitor if any child process has ended and continue with its normal execution. So inside this active waiting at the end, while the number of children is greater than 0, the only thing we need to do here is to sig suspend this process within this mask. So here we just type sig suspend with the mask. With this, the parent process is going to be waiting for the children to terminate. And it is going to be inside this function that we have here, the treat death child, where we're going to use the wait PID system call. So let's define this function here. Remember, as any function treatment for a signal, we always need to follow the same format. It must be a void procedure, okay? It mustn't return anything. And this is, the name can be any name, and this, very important, needs to be an integer value, because this is the signal code that we receive, which is an integer value, right? So let's name this to be void. This is the death, or the treat death child, right? This is the treat death child, as we have called. This is the signal that we receive as, And so what we are going to do inside this treatment is to execute the wait PID. So here we can just type two variables, the wait PID. We can use here the PID returning value of the wait PID, then the result that we pass as the result information of how this child has finished. So here we use the wait PID system call. So PID is going to be equal to wait PID. We are going to wait as before for any child to finish, right? Here we want to pass the result information, although we are not going to use this result information. Okay, we pass this integer value since it contains information about how the child has finished, how the child has terminated. And so what is very important here is that we, okay, shall not make the parent to be blocked. So the wait PD function without blocking the parent process needs to be executed. So to make sure that this happens, that the parent process will not be blocked, okay, there's here a special argument in the last argument here, which is the with no hang, as we can see, with no hang. So this argument, what specifies it is an option of the wait PID. The last argument, the third argument, is the argument for the options. And here with the with no hang option, what we do is we check if any child process has ended without blocking the parent. Okay, so with no hang, we do not block this parent process. So remember that this PID, when a given child finishes, this PID variable, the returning value of the wait PID, is the PID, the process identifier of this child that has finished. So the wait PID on success returns the process ID of the child whose state has finished, right? Now, if we have the with no hang option, and if with no hang option was specified, and one or more children specified by the PID, in this case, since we have the specified PID minus one, it can be any children, okay, but they have not yet changed the state, then the 0 is returned. So this PID here, okay, returns one of three possible values. First of all, if no child process has terminated yet and the with no hang option is set, the wait PID returns 0. If a child process has terminated and the parent process has successfully waited for it, the wait PID returns the process identifier of the terminated child. Finally, if an error occurs, the wait PID returns -1. So here, if we basically do a very simple loop while the PID is greater than 0, with this expression, this PID will either return 0, so be a 0 number, or a positive integer when a child process has terminated. So if the value is 0, it means that no process has terminated, so we are going to leave this loop. We are not going to execute the body of this loop, otherwise we are going to enter inside. So remember, if there was an error on the wait PID, of course, no child process, okay, was notified to be terminated because it was an error on the system call. In that case, we are not going to go inside this body of the loop because the condition is that the PID needs to be greater than 0. If the value of the PID is 0, it means that we're waiting, but yet and not yet any child process has finished. So we are not going to execute the body of the loop. Finally, if any child process has finished, we will have inside the PID this PID of the child, which is always a positive value, and so we are going to go inside this case the body of the loop. So in this case, we will go inside the body of this loop. So it is only when a given child terminates that we enter this body. And what we do here inside this loop is precisely the same as before. We can define a buffer. Okay, let's declare this buffer of this size in bytes. We can save inside this buffer this message with this printf. Let's just say ends or terminates the process, and here we specify the PID of this process. We also add an end of line at the end, a line break with the \n. So remember, we can get the PID of the child that has terminated with this variable. Of course, this variable contains the PID, the process identifier of this child, right? So we just type here, we close this quote, this double quote, the PID, right? So we substitute this value which is a decimal value with this integer, right? So with this, we are not writing through the console, we are merely saving this message into the buffer. So if we want to write this message in the console, we need to use the write system call with the standard output, which is the channel 1. Here we have the buffer, here we have the length of this buffer, so we want to print all of the bytes of this buffer, so we can use the string length method, right? And also we need to here decrement the number of children. because this child has terminated. So we have one less child alive, okay, in this structure of the processes. We also need to increment the counter. It means that we know that one child has been created before since this child is terminated. And finally here, we need to do the same thing with the wait PID. So we again call the wait PID with the same arguments, right? We wait for any child. We leave here the state of how the child has terminated inside this variable that we pass as reference. And finally, the options argument is with no hang option. So if no child has terminated, this returns 0. Yeah. So very well, we close this loop. We close this treatment of the sick child signal. Let's also comment here, treatment of the sick child. Very well, so with this we have the example signal program implemented. And also very important, remember that these variables, the variable for the counter and the variable for the children, they are local variables inside the main function. So if we want to use them outside the main function, okay, here, particularly inside the treatment of the sick child, we need to make these variables to be global variables. So here we just, we can get this from the local main function, and we define this at the beginning, for instance, in here, the counter and the children integer variables, right? So with this, we are able to modify those inside the treatment of the sick child. What is also very, very important is that at the end, okay, when we have here this for loop, and we are basically differentiating the cases between the child process, if we have an error, okay, and so on. In the same way, we can see here that inside this for loop, we can consider the case that we are the parent, okay? So if the PID is not 0, okay, if this fork returning value is not 0 and neither -1, it means that this fork, this PID value is a value greater than 0, which is the PID of the child that is returned to the parent. So this is the code of the parent, right? So here we can basically see this is the parent code. So what we need to do inside this parent code, very, very important not to forget this is key, is we need here to define the mask that we are going to use inside the sick suspend. So what we are going to do is we are going to create a mask with all of the blocked signals inside. So essentially here, DSA, we can use the SA mask, for instance, SA mask. And then we need to here, very important, delete from this mask. We need to delete from this mask the sick child, because we want to be able to receive this sick child in the parent process and to treat, right, this sick child inside this function. So we don't want to block this signal, right? We want here to unblock this signal. So we can just delete, okay, from this set, the mask, okay, that we have here, and we can basically set here the sick child. So we have two things. One thing is we fill all of the mask blocked signals inside this structure sig action that we handle. And on the second thing, we need to here delete from the mask, which is a local variable inside the main program, right? Remember this mask that here we have. We need to delete from this mask the sick child signal, so we unblock this signal and we are able to treat it. Keep in mind that at the end of the sick suspend, the parent process is going to be waiting inside the sick suspend. What is the mask of this sick suspend? This one. Okay, which signals is going to be blocked? Well, the ones we have inside the mask, but not the sick child, because with this instruction, we are deleting, we are unblocking the sick child from the mask of blocked signals. So here we are basically unblocking sick child. So now we will be able to receive the sick child in the parent process, and the parent process will be able to treat this signal. Very well. And with this, we are done. We can now, even here on the treatment of the sick child, we can print here something at the beginning of this treatment. We can make this, okay, declaration to come here at the beginning. And here we can use the printf. We can type something like sick child treatment. We add also a line break, an end of line. Here we save this, okay, and then we write on the standard output. We can write on the standard output we're using the channel 1. Remember, the 1 is the channel for the standard output, right? We are going to write this buffer here with this size, which is basically the size with all of the bytes of this buffer, and we are going to write this onto the console. So we are going to be able to see when we here arrive to the sick child treatment. So here with the terminate process, we can also able to see it, but since in the wait PID we also saw this message, now let's even add that we are inside the sick child treatment, right? Remember, this is going to be displayed always whenever we enter here the treat death child, which is here the treatment of the sick child. Whenever a child process finishes, this sick child is going to be sent to the parent, okay, by the kernel. We are going to print this, right? And we are going to basically keep here inside while the children keep finishing. So once the child doesn't finish, we are not going to print this anymore. So let's here see how this program behaves. So let's go to the console. And also here before, let's saving inside this is printf the buffer. So we are going to be basically saving this string message inside this buffer. So this information in bytes inside this buffer. And then we are going to write into the standard output, right? And now let's compile this program. Let's see how it all works and let's analyze its behavior. So first of all, we open our terminal. We can list the contents of this folder. Now we can see we have the example signal. Let's compile this program. Let's just name the executable to be the same as the name of the file, signal.c. We compile it, okay. We can now list that we see here we have the example signal executable file. And so now let's run this, okay. So we just type point a slash, and here we type example signal. Okay. We press the enter key, and what happens? Well, as we can see now, okay, the parent process basically tells us the same message as before, creating child number 0, creating child number 1, and so on. The children keep here printing hi, I am, and the PID of this child, and so on. And then we reach the sick child treatment, as we can see. So we reach the sick child treatment, and as we reach, we can see that here we terminate the process 464, so the child with the PID 464, then this one terminates, then no one terminates because we leave the sick child, then we enter again the sick child signal treatment, as we can see, and then it terminates only this one. Then no one terminates, we leave the sick child, right? And then we enter again. So this is an example of the wait PID, an active waiting without blocking the parent process. This is very important, okay? This part is very, very important. The problem statement specifies that we need here to do an active waiting and a wait PID on the parent process without blocking this parent process. So the parent process will able to leave this wait PID. And this is of course what is happening here, because we're using the with no hang option, right? So if no children, okay, has finished, then what we do here is essentially we don't enter inside this loop, right? If no child has finished so far, we are not going to enter inside this loop because the with no hang option, this wait PID is going to return 0. So since the value of this variable is going to be 0, we are not going to go inside this loop. We are going to leave this treatment of the sick child. Then we are going to go in the sick suspend, waiting again for the children inside this loop in here. Once a child has terminated, we enter again, and when we enter again the sick child treatment, and so we terminate this child. If no one terminates, we leave the sick child, then we wait on the sick suspend, okay, and then again we enter the sick child treatment because the sick child has been received. It means that one child has finished, right? So we basically enter inside the sick child treatment, and so here we can see how the children terminate, right? And at the end, as before, we see here the value of the counter. This is merely information of how many children we have created so far. Very well, with this we end the solution to this problem 8 and the solution to this implementation of the example signal program. We remind the student that you can download both the statement of this problem as well as the solution on the downloadable documents of this lesson.